Imagine you've got this beautiful glass sphere, or maybe it's a specialized camera lens or a curved mirror. Now, you need to know its exact radius of curvature for an important physics calculation. But, well, there's a huge catch here. You can't cut it. You absolutely cannot break it. And your standard flat rulers? Yeah, they're completely useless for this. So how do you actually measure the exact dimensions of a curved, three-dimensional surface without totally destroying the object? Welcome to The Explainer. Today, we're going to solve that exact problem by mastering what is honestly a brilliantly simple yet incredibly precise instrument. Meet the spherometer. It's essentially the micrometer-based hero of our Class 11th Physics Lab practical. It's your go-to tool for measuring the radius of curvature of spherical surfaces, and by the end of our time together, you're going to know exactly how to use it like a pro. Here is a quick roadmap for our virtual lab practical today. First, the spherical measurement problem. Second, anatomy of a spherometer. Third, pitch and least count. Fourth, the lab practical steps. Fifth, calculating the curvature. And finally, avoiding common lab errors. Let's get into it. Section 1, the spherical measurement problem. Okay, let's dive straight into this. In physics and optics, knowing the exact curvature of lenses and mirrors is, well, it's fundamental. Whether you're deriving focal lengths using the lensmaker's formula or setting up some massive complex optical array, even a tiny error in curvature completely throws off your entire experiment. We need a reliable way to measure a 3D curve using a flat 2D reference plane as our baseline. Picture a real-world spherometer resting on a plain glass plate. It works strictly on the principle of the micrometer screw. I mean, the name literally gives away its job, right? It's a spherometer. By resting simultaneously on a curved surface and adjusting its center, it measures this incredibly tiny vertical distance, and we then use that tiny vertical distance to mathematically reconstruct the entire sphere's radius. Moving right along to Section 2, anatomy of a spherometer. Listen, if you're going to use an instrument in a lab, you need to know it inside and out. You want to be completely confident when you're taking your readings. It's a remarkably perfectly engineered device. It features a metallic tripod framework, and it's supported on 3 fixed legs of equal length. At their tips, those 3 legs form a perfect equilateral triangle. Now, right in the middle, passing parallel through the center of that triangle, is a threaded central screw. Attached to the very top of this screw is a large circular disc graduated with 100 equal parts. That right there is your circular scale. And fixed alongside it is a small vertical scale, divided into millimeters, which we call the pitch scale. Section 3, pitch and least count. Before you even think about touching a glass slab or a lens in your practical experiment, you absolutely must calculate your tool's mathematical constants. These are the numbers that determine the precision of every single reading you'll take today. First up, we have the pitch. The pitch is simply the linear vertical distance that the central screw moves when you give the circular scale exactly 1 complete revolution. To find this in the lab, you just note your starting point on the vertical pitch scale, give the disc, say, 5 full rotations, and measure the distance moved. If 5 rotations move the screw 5 millimeters, well, your pitch is exactly 1 millimeter. It essentially represents the physical thread distance of the central screw. So, the absolutely crucial point here is how we use that pitch to find the least count. The least count is literally the absolute smallest measurement our spherometer can accurately record. You calculate it by dividing the pitch, which we just found to be 1 millimeter, by the total number of divisions on the circular scale, which is typically 100. 1 divided by 100 gives us 0.01 millimeters. Just think about that for a second. That is incredible precision. We are talking about measuring distances down to 10 to the power of -5 meters. Section 4, the lab practical steps. All right, our constants are locked in. Let's get to the really fun part and conduct this virtual experiment together, step by step. Your first step is actually performed on a piece of paper, not on the glass itself. You'll place the spherometer on your practical notebook and gently press down to get the physical pricks of the 3 fixed legs. Just mark those indented points, A, B, and C. By joining them up, you form an equilateral triangle. Then you measure the distances AB, BC, and AC with a ruler and take the average. This gives you the mean distance between the legs, which we mathematically denote with a lowercase l. Now we run into a fantastic lab term, sajida. I know, it sounds a bit intimidating, but honestly, it is just the physical height we need to measure the curve. Specifically, it's the distance of the central screw tip above or below the flat plane formed by the 3 fixed legs. When your spherodometer sits on a convex lens, that middle leg sits higher than the outer 3. That tiny height difference? That's our sajida. denoted in all our formulas as lowercase h. So how do we actually find h in the lab? It's a pretty straightforward three-step process. First, place the spherometer on a flat glass plate. Lower the central screw until the tip just touches its own reflection in the glass. You take the main scale and circular scale reading, and boom, this is your flat zero reference. Second, move the instrument onto your convex surface and repeat the process, lowering the screw until it touches. Take your new reading. Third, you calculate the difference between these two readings. The numerical difference between the flat plane reading and the curved plane reading gives you exactly h, the sajida. Section 5. Calculating the curvature. Okay, so we now have our leg distance L and our height h, which brilliantly illustrates the pure elegance of physics. We use a specific formula for the radius of curvature, capital R. It is equal to L squared over 6h plus h over 2. And hey, this formula isn't just magic. It is derived directly from the Pythagorean theorem applied to the cross-section of our sphere. By simply inserting our measured mean distance between the legs, L, and our measured sajida height, h, we calculate the exact radius of the complete sphere that our curved surface was originally cut from. It's like solving a giant puzzle with just two tiny measurements.
Section 6. Avoiding common lab errors. Now, you can have a perfect mathematical formula, but that doesn't guarantee a perfect result if your physical data is flawed, right? So here are your critical precautions for the lab. First, ensure the screw moves freely. Friction is literally a silent killer of a good physics grade, causing the instrument to stick and give you totally false readings. Second, always check for zero error on a flat surface. If the instrument doesn't read exactly zero when flat, you must algebraically add or subtract that baseline error from your final reading. Third, never force or over-rotate the screw once it touches the surface. Otherwise, you'll accidentally lift the three fixed legs right off the glass. And finally, you must heavily beware of something known as backlash error.
Let's look a little closer at backlash error. This is a measurement discrepancy that's caused by the mechanical play or the slack in the screw threads themselves. Basically, if you turn the screw down, miss your mark, and then try to turn it slightly back up, the threads shift slightly before they catch, and that gives you a completely inaccurate reading. To avoid this entirely, always turn the screw in only one direction when taking a measurement. If you overshoot your mark, back up well past it and approach it again from the original direction. Well, we did it. We successfully measured the invisible curve of a sphere using absolutely nothing but a threaded screw and some really clever geometry. The micrometer principle we used here today isn't just for high school class 11 labs. It is literally the fundamental foundation of modern manufacturing, aerospace engineering, and advanced optics. Which leaves us with a pretty exciting question to ponder. How else might micrometer principles be used in modern precision engineering? Think about the devices you use every single day that rely on perfectly curved glass or microscopically precise moving parts. Keep observing, keep questioning, and I will see you in the next explainer.